István and András. Hello, guys. Or hello, István.
Hello.
I think you're only one. Hello, how are you?
Absolutely ready to present.
Awesome. So yeah, as I was telling earlier, there seems to be some very cool demos from your side. So the short name of the project is, I'm not sure how you pronounce it, but I think you spell it Modest 3, as in model-based MO demonstrator, DE, S for smart and safe systems. So triple S. So yeah. Why don't you tell us more about what you've been building during the Open IoT Challenge? I think it's in actually 2 projects that you guys built, but they are interrelated, sort of. They're based on some common technologies, right?
Yeah. Okay, so my name is András Vörös, and with my colleague István Ráth, we will tell about model-based demonstrator for smart and safe systems. So what is the goal of our project? So traditional safety critical systems apply model-based development. Various validation and verification techniques are used. Code generation are applied, and also many safety requirements are against the systems. And on the other side, there are the so-called cyber-physical systems, where we have various information sources from sensors, and they are inherently heterogeneous. So there are embedded computer sensors, and also cloud computing is applied. And our demonstrator is a combination of both worlds. So we used development techniques from the safety critical domain, and we combined them with technologies from cyber physical domain. So it's kind of a mixed critical system. So let's start with a video, just introducing the working. Do you see it? Hopefully.
Yes.
Okay. So this is a short introduction of our project. So you can see the first steps when we developed the distributed logic, and it is tested in the cloud. We have also this robot, which is responsible for moving, lifting, and moving objects from and onto the trains. And in the next video, you will see how computer vision helped the robot control.
So you're using OpenCV, right?
Yeah, I will discuss it more detail. Is just the physical, the working of the physical system. So, and it also handles human intervention. So if I just take my hand there, it just stops successfully. And the main purpose was to develop safety logic, which stops the trains. So when they reach the same section, the same part, the safety logic will stop the trains. And just a short video about the high-level monitoring based on complex event processing. So you can see that we used computer vision, and we also developed a client to depict what happens in the system. So it is on the left side. So let's go a little bit into the details. So we have a robot system for moving and removing objects, and we also have a railway system for transportation. So this is the high-level overview. In the middle, you can see the hardware, and on the bottom, you can see the distributed safety logic for ensure the safety of the railway system, and above the system we have a monitoring and control logic. So let's start with the railway system, where we have various sensors and actuators. So we built this small system with 15 sensors responsible for sensing the trains and estimating their locations. We have also 6 embedded controllers, actuators. You can see the bottom of this system, where you can see these embedded controllers. Actually, these are Beagle-bone boards, and we used 6 of them, responsible for ensuring the safety at certain parts of the system. And we developed a distributed safety logic with the help of the Yakindu state chart tools. We developed validation techniques with the help of VR query, which helped to ensure the correctness of the safety logic. We also developed verification techniques based on model transformations to verify the correctness of the individual components of the system. And we used code generation from the Yakindu state chart tools to produce the implementation. So each implementation was deployed into a dedicated controller, which was responsible for a track section, and it controlled it. And we used various IoT technologies for communication, like Eclipse, PAHO, Mosquito, to establish the communication between the components. So let's go further. Let's continue with the monitoring and control system. We implemented an additional level of safety with the help of a high-level monitoring system. We used computer vision, so we deployed a camera system on top of this small of this table, and we used this MQTT technology and sent this information to a monitoring component based on complex event processing. And we specified the requirements in the VIATRA event processing language. This requirement was to shut down the whole system in case of dangerous situation. We compiled these rules. We produced the monitoring logic, which was then executed with the help of this VIATRA CEP. So we deployed all this logic into the cloud, and we use various open source technologies, for example, Node-RED, to establish the communication and the configuration in a model-based manner. So let's continue with the robot system, where the goal was to remove objects from the trains. So place onto other trains or place onto the ground these objects which were transported. And we also developed this control logic with model-based tools. We generated the implementation, and we used actually the sensor information and computer vision techniques to provide feedback to the controller and to ensure the safety, and actually ensure that it just do what we want, defined in the control logic. So actually the goal of this demonstrator is to apply it in the education in various courses. So we plan to apply it in our cyber physical systems course, in model-based system design course, in system modeling, and also in our formal methods course. And also I have to mention that our team is mainly built from students. So there are 2 MSc and 7 BSc students in our team. And we also plan to apply it in our research at the fault-tolerant systems research group and the MTA BME research group on cyber physical systems. And we also had some industrial sponsors Inquiry Labs Ltd, Quanopt Ltd, and Ericsson. And just to summarize our work, the use technologies actually in this complex case study, we applied about 20 different technologies from the open source world. And thank you for your attention. And if you have any questions, please let us know.
Thanks. That's definitely a huge list of projects that you used. So let me see if there are any questions. I think I just saw actually a tweet. What are the next steps for your project? By the way, are some of the pieces of the project open source?
In fact, all of the components are open source. Yes.
Okay. And so do you think it's easy for anyone to actually replicate the exact hardware setup?
Well, the hardware is actually, I think, more difficult to replicate than the software itself.
Yeah.
Because it's a rather complex system, as you might have seen from the photos.
Yeah.
But we plan to produce a comprehensive documentation, at least for the most critical parts. So if there is anyone interested, then we can turn it into a sort of open hardware project as well, because we believe that there is a lot of opportunity, especially for educational purposes.
Okay. So there is a question from Julien on Twitter. Some of the technologies you used, like Node-RED and MQTT, Mosquito, maybe OpenCV, do you think they are actually safe for building a safety system? And if they're not, are there better technologies, or is there anything that could be improved in terms of using different protocols, using different brokers, different programming environments?
Yeah, this is actually a very good question, and this is basically the most important research question of mixed criticality systems, whether you can assemble something which is safe from components that are inherently unsafe, such as the open source technologies that you mentioned. And this design is basically meant to illustrate how such a system can be designed, where you combine, let's say, rather conservative technologies with state-of-the-art IoT technologies, and you use validation and verification techniques, which are not necessarily detailed in this short presentation, in order to verify that individual components as well as the system as a whole, fulfills safety requirements.
Okay. And do you actually provide a way to model the actual underlying network and I guess the internet itself, in that part of the safety is that you want your queries to reach a server in a given time, otherwise it's too late, right? So is this part of the whole solution to model that whole aspect?
Yeah, it's actually not highlighted that much in this presentation, but the goal of choosing state charts as the modeling language and Yakindu as a tool specifically was exactly to have a very concise and formal way of capturing the essential operations of the system. And these models were in fact not only used for code generation, but also for verification purposes. So we used some formal methods, tools to verify the safety properties of the system. We plan to produce some papers on this topic in the near future. So if there is anyone interested, we would be glad to share the details.